Okay, so today's notes are on exponential models, and our content objective is to model exponential growth and decay, and our language objective is to use the correct terminology to describe exponential functions and their behavior. So the first thing I want to do is define exponential functions. So exponential functions are functions in the form y equals a times b to the power of x, where a does not equal 0 and b is greater than 0 but not equal to 1. So just a quick recap why that is. If a were 0, that would cancel the whole thing, so we would just have y equals 0. B has to be greater than 0 because if we plugged in a negative number, we'd get a weird alternating thing depending on if x were or even or odd, because if it's a negative to an even power, it wouldn't be negative. Negative to an odd would be negative, so it would be a weird back and forth that doesn't work. And b can't be 1 because 1 to any power is still 1, so you'd still end up with just a flat line y equals a. Knowing all those details is not critical right now, but that's a quick recap of why. So I want to jump into an example of what this will look like. So I want us to start by graphing y equals 2 to the x. So I want to note here, in this case, since there's nothing being multiplied by 2, it's a would be 1 and b is 2. So just so you can connect it to the equation we just saw. And we're going to start by making a table to sort of see what we get for values and how this will all work out. And I'm going to show you the work for each one when we plug it in here. So I'm just going to make an easy table, -2, -1, 0, 1, 2. So pretty simple numbers for x, and I'm going to plug them into our equation here. So I get y equals 2, and I'm plugging in -2 for x in the exponent, so I have 2 to the -2. As we know from our negative exponent rules, that's equal to 1 over 2 squared. 2 squared is 4, so I end up with 1/4 as my y value there. Again, because negative exponents flips it into the denominator, so I end up with 1/4. I'm going to do the same thing with 1, so now I have 2 to the -1, which I know actually becomes 1 over 2 to the 1, which is just 1/2. Now I plug in 0, I get 2 to the 0. Anything to the 0th power I know is 1, so I end up with just 1 there. And if I keep going, now I have y equals 2 to the 1, that's just y equals 2. And last but not least, if I plug in 2, I get y equals 2 to the 2, which I know is 2 squared, or 4. So I want to note a couple little things here. First of all, we end up with, as we plug in negative exponents, we end up with fractions. So notice that we're not getting negative numbers, but we're getting fractions as we plug in negative values for x. The other thing is these are kind of inversely related in that this is 4, 1/4, 2, 1/2, so they kind of become the fractions on the other end. So then we're actually going to graph it. Since I don't have any negative values, I'm not going to worry about the negative side of that, and I'm going up to 4, and then I just have -2, 0, 1, 2. So if I plot this, I end up with -2, 1/4, so I'm going only 1/4 of the way up, so it's pretty close to the x-axis. Then I'm going to 1/2, 1 at 0, at 1 I'm at 2, and then at 2 I'm at 4. So I end up with a graph that looks like that. And this is the general shape of all the exponential functions we're going to be, or all exponential functions. So they generally take this shape with an asymptote, which we'll talk about in a second, and going up on one side. Our domain here, there aren't any x values we're not allowed to plug in, so it would be all real numbers. So we can plug in negative exponents all we want, we're just not going to get negative numbers. So we can plug in any values for x, no problem. Our range, however, as we noted earlier, even as I plug in negative x values, I can't get negative y values, I just end up with fractions. So what ends up happening is it gets really close to this x-axis, which we're going to call an asymptote, and I'll talk about that more in detail in a minute. But since it won't ever go below this line, or we'll just keep getting smaller and smaller fractions, my range is going to be y is greater than 0, because it's never going to quite touch 0, but it'll get really close, and then all the other y values are clearly going up, so it's all y values greater than 0. All right, I'm going to do another quick example of this for a slightly different function. So here we had an a or a b value that was greater than 1, but now I want to try graphing one where our b value is less than 1. So y equals 1/3 to the x. Here again, a is equal to 1, but this time b is equal to 1/3, just if we're connecting it back to that equation. So again, we're going to make a table. So I have my x, I have my y, and I'm going to show you the work for each one. So here I'm going to plug in the same values, -2, -1, 0, 1, 2. When I plug in -2, I have y equals 1/3 to the -2. That means I distribute my exponents. So I have 1 to the -2, 3 to the -2. As we were practicing before, when I have a negative exponent, I actually flip them. So I end up, to make the exponents positive, not the bases, the exponents. So I end up with 3 squared over 1 squared, which is just 9 over 1, which is 9. So if you notice that, the negative exponents flip it and end up making it positive. If you can't see this, this is a 3 to the -2 up there, but that's what we get. So then if I do the same thing with 1/3 to the -1, I end up with 1 to the -1 over 3 to the -1. In order to get rid of those negative exponents, I flip them and I get 3 to the 1 over 1 to the 1, which is just 3 over 1 or 3. So notice that when we have a fraction, we end up flipping it basically when we plug in negative exponents and getting larger integers. Now if I plug in 0, I know anything to the 0th power is just 1, so that's just going to be 1. And then now I start plugging in my whole number exponents. Anything to the first power is just the original number. So when I plug in 1, I get 1/3. And then when I plug in 2 for x, or for the x value, I get y equals 1 squared over 3 squared, which is 1 over 9. So notice that my table is sort of, when I have a value less than 1 for b, I end up with higher values on the left side of the graph and fractions on the right side. So we're going to graph this one as well. So I have -2, -1, 0, 1, 2. And this time I have to go up to 9, so I'm going to make a little smaller scale. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So at -2, I go to 9. So I have a point there. At -1, I'm at 3. 0, I'm at 1 still. Then I'm at 1/3, and then 1/9 gets super close. So we end up going more steeply down. Still make sure that your line doesn't cross that x-axis because it never actually does. So notice when we have a value less than 1 for b, we end up going down from left to right. When we have a value greater than 1 for b, we go up from left to right. And so this actually models what we're going to talk about next, exponential growth versus exponential decay. So I'm going to flip the page and sort of more clearly define those two things. So if we're talking about exponential growth first. So exponential growth, it's when our b value is greater than 1, which means, and y increases as x increases. So they go, as one goes up, the other goes up. So in more simple terms, goes up from left to right. So just a quick sketch of an exponential growth graph. Very quick sketch. It's just going to look like the other one we had, x-axis, y-axis. It's going up from left to right. On the other hand, exponential decay is going to be the opposite. So in this case, b is going to be less than 1. Again, it still has to be greater than 0, but your b value is less than 1. And this time, y decreases, or your y values go down as x increases. So again, as I just said, your graph goes down from left to right. So if we do a quick sketch, sorry that got out of the way. It's going to look just the opposite. So it goes down from left to right. And the only other thing I told you we're going to talk about in more detail right now is an asymptote. So all exponential functions have an asymptote. And if it's in the simple form, y equals a times b to the x, your asymptote will always be on the x-axis. So the vast majority of the time, it'll be on the x-axis. But by definition, it is a line that a graph approaches but never reaches. So as we saw with our fractions, when we plug in negative exponents, we're not getting negative numbers, we're getting smaller and smaller and smaller and smaller fractions. But there's no value I can plug into x that I would actually reach 0. So there's no number I can plug into an exponent and get a value or an x output of 0. So that's why we end up with an asymptote, because there's no way we'll ever actually get that value of y equals 0. It's just going to get infinitely closer, which is what we call an asymptote, when the graph gets infinitely closer but never quite reaches a particular value. So in this case, since we can't ever get 0 by plugging in an exponent, when we plug in values to an exponent, we're going to end up with an asymptote at y equals 0. So I want to do a quick summary of what we've done thus far before I delve into the last thing we're going to do. So our key points for today are, for the function y equals a times b to the x, if a is greater than 0, meaning is positive, and b is greater than 1, the function represents exponential growth. On the other hand, if a is still positive or greater than 0, and b is less than 1, the function represents exponential decay. In both cases, so I'm going to start. In both cases, your y-intercept is 0, comma a, because when I plug in 0 to the exponent, it's anything to the 0th power is 1, which leaves me with a. So when it's in this form, your y-intercept is always going to be 0, comma a. So whatever your a value is will be your y-intercept. The domain is all reals. And the asymptote is on the x-axis, or when y equals 0. So the range has to be y is greater than 0. So those are the key, that sort of summarizes what we've gone over thus far. I'm going to do a couple of quick checks. So I want you to identify as growth or decay. So tell me if each of these functions is exponential growth or exponential decay. I have y equals 12 times 0.95 to the x, and y equals 0.25 times 2 to the x. Sorry, that's in the exponent, ran out of space. So I want you to identify these as growth or decay. Pause it if you need to. I'm going to go over it. So in this case, I see my b value is less than 1, so it's going to be decay. In this case, my b value is greater than 1, so it's going to be growth. So growth and decay, decay, growth, all you're doing is looking at the b value and deciding which one is which. Okay, last thing, I'm going to try to go over this super quickly, or as quickly as possible, but the equation for exponential growth or decay, I might have to save the example to do together in class for the sake of time, but how are we actually going to use this information to model growth and decay? Well, you can use an equation. So the equation is a of t equals lowercase a times 1 plus r to the t. So again, make sure you properly label capital A and lowercase a. Those are two different things. That's why I say make sure you're always using the correct capitalization. So first thing, capital A is the amount after t periods. So we're going to be working with time here. So our capital A value represents the actual amount after t periods. T, as you might guess, represents, so both of these are t. These represent the number of time periods. A is our initial amount. and R is our rate of growth or decay. It's going to be growth if R is greater than 0, or decay if R is less than 0. So again, if I'm adding a negative, I actually take away from 1, so I'm going to be multiplying by a number less than 1. If R is greater than 0, I'm adding something to 1, which means I'm going to have a value greater than 1, or a b value greater than 1, which means it will be growth. So again, this equation is going to be particularly important. A of t equals a times 1 plus r to the t. All right, I am going to try to do this, or no, I'll save the example for in class, but make sure you have all this down. We're going to go over how to use this when we get into class next time. So make sure you have all this down. We'll go over it then.